And I think we're good to go. So Matteo is a postdoctoral scholar at Stanford University. He got his PhD in physics from Princeton in 2019 and will move to the University of Texas at Austin as an assistant professor in this fall. His research is at the interface of quantum information science and condensed matter theory, with a focus on quantum many-body dynamics out of equilibrium. Let us all welcome our speaker.
Great. Thank you very much for the introduction, and thank you very much for having me speak at this seminar. I will be telling you about some recent work that I did in collaboration with two more postdoctoral fellows at Stanford, Yaodong Li and Tibor Rakowski, and Professor Vedika Kimani, which is this preprint here. And then at the end, if there is time, I will also tell you briefly about a recent work that I posted just last week on a closely related topic. So the topic of the talk is optimizing classical shadows with insights from quantum dynamics, which brings together sort of two interests of mine, which are quantum information theory and dynamics out of equilibrium in quantum many-body systems. And I think that this is a very nice sort of setting in which they come together in a useful way. So let me start by giving some very general background on sort of motivating questions. So as you all know, we are entering an era of quantum technology in which we have various platforms, from superconducting qubits to trapped ions and analog simulators based on ultra-cold atoms, for example, in which we can realize quantum states that are increasingly complex and have potentially a lot of entanglement in settings that are well controlled. These kinds of states can be difficult to simulate classically. For example, in random circuit sampling experiments on superconducting qubits, this is the case. But also more generally, they can be challenging to characterize and benchmark experimentally as well. And being able to characterize these states is useful not only for fundamental science, but also for a range of applications that you might care about. For example, variational quantum algorithms, where we need to be able to measure efficiently some cost function. And all of these tasks require some efficient learning strategy for sort of efficiently learning properties of these states. So in general, the general question of characterizing quantum states is solved by quantum state tomography. And this is the idea of simply reconstructing the full density matrix in its entire representation with all of its exponentially many entries. However, this is, of course, not scalable because the size of this object is exponential. And even if you adopt the most optimal strategy that makes use of coherent access to multiple copies and so on, this still takes you a number of samples that is exponential. So this is not going to be scalable experimentally beyond a few qubit systems. I think the record is something along the lines of 10 qubits. You certainly won't be able to do much better than that. So there is a very strong motivation for trying to identify strategies to learn a compressed description of a state, so that doesn't require this full state tomography, but in a way that is sample efficient in the sense that it requires some suitably small number of copies of the state, so it's experimentally cheap, so to speak, and also computation efficient in the sense that whatever post-processing needs to happen on classical computers is not unreasonable, something that we can do in polynomial time. And so this is a very, very general question, but a concrete step in this direction that is from a few years ago is this idea of classical shadows, which is a kind of a breakthrough in this direction. And the idea is to learn many properties of a quantum state from some small number of experimental runs by making use of randomized measurements. And this brings together a few prior developments in shadow tomography, which is a more formal sort of quantum information theoretical topic, and randomized measurements, which is an experimental technique that had been developed on trapped ions a few years prior, and brings these ideas together in a very kind of interesting way. And the idea is essentially to take your state, measure it in a random basis, feed all of this data to a classical computer in such a way that you can kind of glue together all of these outcomes of these random measurements and somehow get some description of this high-dimensional object, that's the quantum state rho, from these lower dimensional snapshots that are your various random measurements. And the really striking property is that you don't need to know in advance what kind of property you want to know. You can just kind of blindly form this shadow, the classical shadow of the quantum state, and then later on you can go in and ask different questions that were previously unspecified, and you can answer many of them from some finite number of some small number of measurements. So to give a concrete example, here is here's a list of a few things that you might want to know about a quantum state. First of all, expectation values of linear operators. This is the case of order parameters or energies in many body states, or cost functions in variational algorithms and so on. So obviously very, very important. Also, a special case of observable expectation value is a many body fidelity. So when this operator O is a rank 1 projector, what you get is this fidelity, which you might care about for benchmarking the quality of your, if you're trying to prepare some state psi, you want to know how well you did. This is a kind of thing you might care about. And then also more strikingly, you can learn nonlinear functionals of a density matrix, such as this purity, or also a range of other such functions that are often related to entropy or entanglement properties. And again, you don't have to know in advance. So a really striking demonstration is this experiment from 2019, which you might note is before the development of classical shadows. However, it happened to use the same kind of randomized measurement technique. And so it produced a data set that could then be used in classical shadows. So in this paper, the authors were measuring basically the purity of various subsystems of a trapped ion chain. And then in following years, by using classical shadows, they could then understand various other properties, for example, fidelities, or other types of entropies like entanglement negativity or symmetries of the entanglement and so on. So this is very promising from an experimental point of view, because these experiments are difficult and expensive, and so it's nice to be able to reuse the data and learn many things. So this was my very brief motivational introduction, but in this talk in particular, we're going to talk about mainly this work, in which we look at one particular version of classical shadows that goes by the name of shallow shadows. And we try to understand it by drawing connections to properties of operator dynamics in random circuits, which are an example of kind of more general chaotic dynamics that can arise in quantum systems. And we use this understanding to figure out the optimal depth and the optimal sample complexity of these protocols, which I will explain in the following. And then at the end, if we have more time, I will briefly present this other work in which we look at a different type of classical shadows, which we call locally entangled shadows, that offers a set of simple protocols, much simpler in some ways than shallow shadows, but nonetheless, in some cases, even more efficient. And please, through the talk, if anything is unclear, feel free to interrupt and ask any questions. So in the next few slides, I'll give a brief, slightly more technical review of classical shadows to introduce all the various terminology and notation that we're going to need, and also kind of give some big picture view of these protocols. So the idea in general is that we have this quantum state rho, which we don't know, and we're going to perform some random measurements on it. So the way that this works is that we sample some unitary matrix U from some ensemble that we have to specify, and that's the thing that determines which particular protocol we're doing, and we'll see a few later. Once we choose this rotation, we apply it to the quantum state. So this is something we do on the quantum computer. We do an actual physical unitary, and then we measure. And after measuring, we obtain some, we measure in the computational basis, we obtain some bit string, some string of zeros and ones. That's the state of all the qubits that we have measured. And from this point forward, everything I'm going to say is going to be classical. It's going to be operations that happen on a classical computer. So at this point, we want to somehow guess the state rho based on the data we have, which is the unitary U that we have sampled and the bit string B that we have obtained. So the best we can do is at this stage, so right before the measurement in the computational basis, our guess is going to be that the state was simply the projector on this bit string. That's because the only thing we have to base our guess on is simply this outcome of the measurement, and so our maximum likelihood guess is simply this projector. But that means that our guess for the actual state rho, so at this stage, right before the unitary, is going to be this projector. So the projector on the bit string state rotated backwards under the unitary U, so hit by U dagger. And this state is what we're going to call the snapshot, sigma dependent on the choice of U and the outcome B, given here. And this is something we compute classically again. And then we repeat this many times. So we prepare multiple copies of this state sequentially, one after the other. And then for each one of them, we choose a unitary, we obtain an outcome, we prepare the snapshot. And then if we average all of these snapshots, we find this functional that I wrote down here, which is simply the snapshot weighted by this probability of obtaining B on the rotated state. And then we average over the bit string, so we sum over B. And then this integral in the U simply represents the average over the measure on the unitary group that I'm using here. This doesn't have to be continuous. It could be a Clifford ensemble, for example. It could be discrete, but I'm just, for simplicity of notation, I'm using this integral notation here. So as you can note, this is a stochastic mixture of states. So here I have my snapshot and just weighted by some positive probability and summed. So as a whole, what I get is going to be a state. And it also depends linearly on the density matrix rho. So you can convince yourself that this is in fact a quantum channel. So what I obtain here is the action of a quantum channel M on the true state rho. And so if I could invert this quantum channel, I could obtain this this object I'm going to call rho hat, which is sometimes called the inverted snapshot, defined here, which is by construction an estimator of the true state rho. By that I mean that if I again repeat the process many times and take an average of all of these inverted snapshots, then by construction I'm going to find that this is rho. That's because I can take my average inside the application of M inverse by linearity. And then by definition of M, I have that the expectation of sigma hat is M of rho, and then M cancels out with the inverse, and I obtain my true state. So this is good. It means that it's giving us a way of getting at the true state that we care about. Let me also note that both this step and this step, so the preparation of these snapshots and the inversion of M and the action of M inverse, have to be efficiently computable classically. Otherwise, we are, there's nothing useful about this if we can't actually do this on a computer. So these have to be efficient steps, and this will constrain a bit the possible choices for the ensemble of unitaries that we can look at. So at this point, we have some way of getting at the true state rho, but we would like to learn its properties without actually building the density matrix. And that's because, as we said, the density matrix rho is a huge object. It's exponentially large, and if we tried to build it, we would quickly run out of memory on any computer. So we want to get at the properties we care about without actually constructing rho. So I'll just give you an example of how to do this for the simplest case of learning an expectation value of some operator O, so this quantity here. The idea is that for each one of my experimental shots, I'm going to build the state rho hat, and I'm sorry, this is not a state, in fact, it's a matrix, but nonetheless, I can construct it. And I can compute this number, little o hat, defined in this way. And then by construction, the average of all of these numbers gives me the true expectation value that I care about, just from the way that I've defined my rho hat. This means that the quantity that I defined here, the little o hat, is an unbiased estimator of the expectation value that I want, and so that's good to know. That means that the protocol works. But then the practically relevant question is how many shots I'm going to need to learn the thing I want, this expectation value, to within some small finite error epsilon. Because it could be that I get the correct mean, but the variance is astronomically large, and then I won't actually be able to learn anything useful. So I want to be able to get this quantity to within a small constant error. And how many samples I need, just by the usual scaling of basically the standard error of the mean, with this 1 over square root of a number of samples, is going to be given by the variance of this estimator divided by epsilon squared, which is my target uncertainty. So the key quantity that appears in this calculation is the mean of little o hat squared, which is a piece of the variance. And this quantity, it's been defined as the shadow norm. So it's a quadratic function of the operator O, and it turns out that it has the properties of a norm, so an inner product of O with itself, with some particular inner product matrix that we a priori don't know. So the whole point of this exercise, in some sense, is to understand the scaling of the shadow norm for different operators and for different possible ensembles of unitary rotations. And that is what will determine how efficient classical shadows are going to be for some particular learning task. Okay. So again, to recap, the protocol is as given here. We have a state, random unitary, a measurement. We then feed this to a computer. We compute these snapshots. We invert them in this way. We compute the estimators, and we repeat many times and average. And this is going to give us our answer. And the number of times we need to repeat is proportional to this quantity. That's the shadow norm squared. Okay. If that's all clear, then I'm going to give two concrete examples of ensembles of unitary matrices that have been considered in this original paper by Huang, Kung, and Preskill as concrete examples where, first of all, the protocol is doable. So the classical computing steps are straightforward and efficient. And then we have a good understanding of what the shadow norms will scale like. So the first example, which is also the more practically relevant one, which is this random Pauli measurement case, consists of taking your state on the quantum processor and randomly rotating each qubit independently. So there is a single qubit unitary acting on each one of them. And then we measure again in the computational basis. And this is, of course, easy to do in experiment because it doesn't require any entangling operations. It's a single round of local unitaries, so it's easy. And it turns out that the shadow norm of Pauli operators has the scaling shown here. So the sample complexity will be proportional to 3 to the power of k, where k is the weight of the Pauli operator. And by weight, I mean the number of sites on which it acts non-trivially. So that means that this protocol is going to be good and useful for learning few body operators. For example, one body, two body, few body operators that will have, such that this quantity here will be some finite number. If I were looking at some operator that is non-local and extended over the whole lattice or the whole quantum processor, the exponential here would be, extremely bad. So on the opposite side, kind of the completely opposite regime, we can consider measurements that are randomized not only over single qubits, but over the entire quantum system, the entire processor. So here we would have a completely random matrix. Now, if we try to put a generic random unitary here, this would be computationally hard because even just writing down, global unitary is exponentially costly. So we have to take some shortcut. But it turns out we can do so by using Clifford rotations here. So Clifford group is a subgroup of the unitary group that has this property of being efficiently computable polynomial time. However, it matches the completely random, the hard random measure on the unitary group as far as the third moment. So that's all we need for the various quantities that we want in classical shadows. So the Clifford group is good enough. So that means that there is a way of doing this step efficiently and thus randomizing the whole n-qubit system. If we do that, we find that the shadow norm of any Pauli operator, regardless of locality, is going to be 2 to the n, so exponentially big in the number of qubits that make up the system. And more generally, we would have this kind of expression for the shadow norm, which is the Frobenius norm for a matrix, so the trace of O dagger O. And this means that it's going to be impractical to learn any Pauli expectation value, but it's going to be efficient for learning low-rank operators, such as pure state projectors, for instance. So if I cared about a many-body fidelity, this would be the way to go. The issue is that this is going to be, even though it's efficient on the classical side, it's going to be hard to implement on the quantum computer because making such a random global operation is going to require some deep circuit, which in the presence of noise is going to be very difficult to do. So this is not practical. And this has motivated some interest in trying to find ways of connecting these two regimes, so this local randomization to this global randomization, with some kind of intermediate protocols that maybe could get some of the benefits of both of these extremes. And this is where some recent works come in that go by the name of shallow shadows. Here, the idea is to have this basis randomization step that takes place, before our measurements, be realized by a finite depth local circuit. So instead of sort of a single qubit rotation or an extremely deep circuit, we would have something with a tunable depth t that we can vary to achieve different objectives, potentially, to optimize the learnability of different properties. Now here, the thing to bear in mind is that, unlike the previous two cases, this is not such a nice, simple, solvable model. We're going to have to do some brute force tensor network math in order to compute and invert the shallow channel M. But this can be done up to depth that is logarithmic in system size in one dimension. So this restricts us to one dimension for fundamental reasons having to do with tensor networks. And also it restricts us to fairly shallow depth. That's why the name is shallow shadows. And I'm going to only care about constant depth. So we are okay from this point of view. I'm going to think about depth t being some finite number that will be specified later. Okay, so these original papers that first looked at this type of protocol about not even a year ago, they found some surprising observation having to do with the shadow norm of local Pauli operators of some weight k. In particular, they found that the behavior was non-monotonic with the depth t. So at first, the shadow norm, which again quantifies the sample complexity of the protocol, goes down from its t equals to 0 value. Then it hits a minimum, and then it goes up again with some exponential slope here. And if you try to look at the value of depth at which this optimum is achieved as a function of the size k of your Pauli operator, you find that it grows with k, but it grows pretty weakly. So even though this fit is quite limited, there's only a few data points, it's very obviously sublinear, and the best fit that the authors could get was from this kind of polylogarithmic scaling with k. So this, to us was a bit puzzling, because normally when you introduce locality, properties of the dynamics tend to be affected by locality and causality. So normally you might expect that the optimal depth for an operator of size k might be, for example, linear in k, because information might have to locally propagate across the operator for you to find out that the size is what it is, or constraints of this nature. So it was a bit surprising to see this kind of logarithmic scaling, and also the non-monotonic dependence itself was I think quite mysterious, at least to us. And so we wanted to understand whether there were insights from quantum chaotic dynamics that could be used to understand this behavior and even predict the scaling of this optimal depth, or ways of optimizing this kind of protocol for learning different types of operators. So that's what we're going to talk about for the next part of the talk.
Could I just a naive question?
Yeah.
Why did you think about quantum chaotic dynamics in this case? Like, it's something obvious? It's because you're doing this kind of random measurements?
So the idea of inserting some local circuit here is not from us, it's from these previous papers. But once you have such a local quantum, local random circuit, then yes, the idea of, that is a kind of toy model of chaotic dynamics. It's like the most random local thing you can have, and it's thought to have some of the properties of a typical chaotic Hamiltonian that you could find in nature, even though it's, of course, it's simpler and different, right? It's time dependent, it's random, and so on, but properties of entanglement, operator spreading, and so on typically are well described by these kind of random circuit models. So,
okay. And just a little follow-up from a few slides ago. You showed an example of Pauli's. They were going to be local.
Yep.
And then you showed the global measurements. When you're performing that Haar average, this is also going to change its form, right? So
it's going to change the form of the operator.
Because when you're because when you're doing these unitaries, correct me if I'm wrong, but in this case you could just have a one unitary that would encompass all the possible lines there. But in the case of the locals, you're going to have one for each, right?
That's right. Yes.
And you said that in the global case would be like harder to get, like to implement.
In experiment, yes.
And okay.
Yeah, because if you only have local connectivity, typically, think of a superconducting processor, for example. There's only nearest neighbor gates. You want to get a global random unitary. You'll have to run some circuit of depth that is at least linear in the size of the system. And as things scale up, the noise builds up more and more, and this becomes kind of more demanding. So I mean, there is a theory of shadows with noise, but I mean, genetically things get worse, and you want your measurement to be as clean as possible. So high depth is bad. So that's partly the reason of focusing on short depth later on as well.
Okay. Yeah. Thank you.
That's a great question. Yeah.
Sorry, I have a follow-up question for the first one. And so, if you consider the chaotic dynamics, do you mean you are not considering the ideal case? You introduce some noise in the simulation, so that you can discuss the relaxation behavior, something like that. Is that correct?
Not exactly. We're not introducing noise. We have, these gates here are could be random. They don't have to be. So the green gates have to be random for what I'm going to say next. The blue ones could be random or not, but we will, cases that are well understood and solvable will be cases where also the blue gates are random. So everything is random, and we can do some solid analytical theory. So there's, in reality, there's going to be noise, but we don't think about that. And the relaxation that's going to show up is purely from isolated system dynamics. So it's more to do with something like thermalization in an isolated system as opposed to relaxation in an open system, noisy environment. So maybe that will be clearer in a little bit when I get to the details, but it's an important distinction. So this is all closed system physics.
Correct me if I'm wrong. I think you are going to understand the behavior or the structure of the density matrix. So in principle, you do not introduce evolution to the density matrix. You are trying to characterizing them using this kind of Pauli, the operator you apply, like the Clifford or Pauli unitary. So in this application, do you apply the Hamiltonian? I mean the chaotic inside. It means that you introduce the environment effect. So you are actually introducing some noise model. Is that right?
No, so I'm not going to introduce noise models directly. It's more saying that the moment I have local random unitary dynamics in here, there are ideas of operator spreading that have been studied in the context of chaotic dynamics for closed systems that will become relevant to this problem. But this is all happening in an isolated system in principle.
I see. Okay.
It's more to do with, let's say, one part of the system equilibrating with the rest of the system.
Or you mean your applied unitary is only local, and it will have some effect with other non-applied.
Right. So my operator is going to be local in some region here, and as a consequence of this applied unitary circuit, it's going to change. It's going to grow, and its composition is going to change, and that's what I'm going to care about.
Okay, I see. Thank you.
Yeah. Great. Okay. So I think that this will be a little more concrete. in a couple of slides. But let me just start with, okay, so this is a bit technical. I'm not going to go through the derivation. I'll just give you the result and try to unpack it a little qualitatively. But it is a bit technical, so feel free to again interrupt and ask questions. So the main kind of technical result in the paper, this paper, is an expression for the shadow norm of Pauli operators in this kind of setting. So after this local circuit of depth t, excuse me 1 second. So the expression we find is shown here. We have summation over W, which is a Pauli weight, and I'll tell you where it's coming from, of this quantity 3 to the minus the weight, and this pi of W, which is a probability distribution. So this is some kind of weighted mean of this 3 to the minus W, and then it's inverted. Okay, so what is all this and where is it coming from? Let's start from a simpler case that I think is a little more intuitive. Let's consider this whole circuit here to be made of Clifford operations. So these are random Clifford gates on a single qubit, and these are Clifford gates on 2 qubits, for example. So as a whole, this unitary U of t is going to be a Clifford operation, and it's going to map our Pauli operator O into some other Pauli operator O of t. And this O of t is itself a random variable because it depends on the random choice of U of t, but it's a Pauli. And so for each such operator, we can, it has a weight, a uniquely defined weight, which is the number of sites where it acts non-trivially. And for this reason, we can define a distribution, pi of W, that is the, probability of having an operator O of t of weight W after the application of this circuit. Okay. So visually, what happens is something like this, where at t equals to 0, meaning if I don't have any of these blue gates, I only have the single qubit rotations, this doesn't change the weight of my operator O. And that means that the distribution of weights is just a delta function peaked at k. So k is the weight of my initial operator O, and that is just a single number. So the distribution over all the possible weights is only a delta function at that number. But then as time goes on, I'm allowed to do more of these gates that actually couple my operator to other sites. And then, something's going to happen. But then in the limit of depth going to infinity, this becomes a completely random matrix. So if I just do a circuit and I run it for a very long time, it becomes a random matrix. And that means that my output operator, O of t, is itself going to be some random Pauli. So just take one of the 4 to the n Pauli operators in the system are random. And that is going to have essentially at any given site a random choice between identity x, y, and z, chosen kind of completely at random. So with 3/4 probability, there's going to be a traceless Pauli matrix on any given site. And this means that this weight distribution is going to be basically this binomial, or the sum of n binomials of mean 3/4. Binomial means you have a identity with probability 1/4 and non-identity with probability 3/4, and then you just have the same thing on each site. And when you add them all up, you get something that's a binomial. It kind of looks like a Gaussian, centered at 3/4 of n. So this is what happens at t goes to infinity. And then for intermediate t, presumably something connects these two behaviors, and there is a sort of time-dependent change in this distribution, which then affects the shadow norm as a result. And this was for the case of Clifford circuits, but the same thing, sort of with a small adaptation, slightly more complicated definition, also works in general if my circuit is completely arbitrary and I can just expand my operator in a sum of Paulis and define an equivalent thing. So then we can also try to qualitatively understand what is going on here by noting that this is essentially a kind of mean of the 3 to the W behavior of locally randomized measurements. So we saw earlier that if we have a Pauli matrix of weight k and we try to learn it by locally randomized measurements, the sample complexity is going to be 3 to the W. And what is happening here is that I am taking this decomposition into all the possible weight components, and for each one of them, I'm plugging in the inverse of 3 to the w, and then I'm averaging it, and then I'm taking the inverse again. So this process by which you take the inverse and then average and then take the inverse again is, you can call it a harmonic mean. So anyway, it's some kind of average of this factor that depends on the weight, is the take-home message. And really, aside from all the detail, the take-home message is very simple, and it's that we have connected the sample complexity to the dynamics of operator weight, and the lower the weight, the lower the sample complexity. So essentially, we want to understand the behavior, in time during the course of this random circuit of this weight distribution in order to understand the sample complexity of this task. And now we get to slightly more visual explanation that I hope will make things a little clearer. And imagine that we are starting from a Pauli operator which is of this type. So it's some string of k sites in which there are traceless Pauli matrices that are these dark dots. And then everywhere else it's identity. So these open circles. Now we are feeding this operator into our random circuit, and then we are seeing what happens as a function of time. And there are essentially two things that happen as over the course of this evolution. And first of all, we have the process of operator spreading, which is a thing that is very intensely studied in quantum chaos and various topics. And it has to do with the spreading of information in quantum, in isolated quantum systems. And it means that the support of the operator is going to grow. And it's going to grow in a local way because there are only local interactions. So there is some finite slope that is sometimes called the butterfly velocity, BB, that determines the growth of this support. So there are essentially these areas of size VBT that develop on each side of the operator, where now you are also allowed to have non-identity Paulis. And the effect of this is to increase the weight of the operator, because now you can have more non-identities. At the same time, the interior of the operator that started out completely full, so with unit density, at late times, as we mentioned earlier, it's going to approach the equilibrium distribution of a random Pauli operator. That means that on every side you're equally likely to have identity X, Y, or Z. And that means that the average density is going to be closer to 3/4. It's going to decrease from 1 to 3/4 everywhere in the interior of your operator. And so this tends to drive the weight down. So we have these two processes, the spreading, which grows the weight, and the relaxation that decreases it. And the whole issue of the efficiency of this protocol is going to be determined by the competition between these two things. So to try and understand this, we can have a very kind of qualitative physical picture, which is based on the fact that the spreading is happening only at the boundaries of this operator. So we are in 1D, so there are only two endpoints, left and right, or up and down, and each one of them is spreading and raising the weight. However, the relaxation is happening everywhere in the bulk, and so its contribution is going to be extensive in K. It's going to be proportional to the length of the operator. And so for a big enough Pauli, where K is taken to be sufficiently large, then the relaxation is going to be dominant at the start. So if you think, for example, of the time derivative of the weight, it's going to have a positive constant term from the edges and a negative extensive term from the interior. So that's what's going to win at the start. And that's what determines this decay at early times. And then after a while, when the interior of the operator has reached equilibrium and we have essentially a random identity X, Y, or Z on each site, this is simply going to continue growing. And then the weight at that point is just going to go up to infinity, or to something that depends on system size. And so the optimal depth T star of K is going to be determined by the balancing of these two processes. And that's what we want to understand next. Okay, so to get some analytical understanding, we took a particularly simple case. Again, as I said, the choice of dynamics you could put in there is quite arbitrary. It could be a Hamiltonian, as long as you are doing random rotations before and after. But it's simplest to analyze if the whole circuit is made of hard random gates. Then we can really solve the problem in some detail. And in particular, what we want to understand is the relaxation of this, what we call Pauli density. So that's just the probability that each site has something that's non-identity, x, y, or z, as a function of time. So again, this has to go from 1 to 3/4, but we want to understand how it does so as a function of time. And this is something we can solve analytically in hard random circuits in one dimension with I think a very kind of elegant and nice mapping to a problem of a statistical physics of random walks. So the details get a bit technical, and I'll refer you to the paper again. And we're also using ideas and techniques that were developed previously in some other works on dynamics in random unitary circuits that have such random walk mappings. But the point is that we have our initial operator, which is completely full of traceless Paulis. There are these dots. Then there is our circuit, and then we are essentially trying to calculate the density at site I. And it turns out that the calculation maps onto this problem where you have two particles, two random walkers that are initialized at the sides of this site of interest. And then whenever they encounter a gate, they can hop left or, they can hop up or down in this case, with some probabilities that are that you can compute and that have a bias in favor of the walkers spreading outwards, it turns out. And then the quantity you want, this average density on some site as a function of time, is the survival probability of these two biased random walkers up to the time t, which is the depth of this circuit. So I'm showing you here two instances, one in which the walkers happen to kind of collide, and when they do, they annihilate, and this is the end of this diagram, and this doesn't contribute to this quantity. And on the contrary, when they avoid each other for long enough and they make it to the other end, then this is a contribution to this quantity. So in the end, based on this mapping, we can, this is a solved problem we can just look up, and there's a good understanding of what happens. And this is what we find. So we have that the asymptotic t goes to infinity limit is this expected 3/4, but the approach to it has this exponential dominant behavior with a rate that we can compute, but also it has a universal power law, t to the minus 3/2, multiplying it, which comes from, exactly from this random walk picture. It's a signature of this sort of the statistical picture of random walks that are, such power laws often come out. And it's not, not physically super important because ultimately the dominant piece is the exponential, but it's going to show up in an interesting way. So I just want to flag it. And then now we can, with this knowledge, we can go back to our result about the shadow norm, and we can try to actually understand what the shadow norm is going to do as a function of time. So here we have again our result, and we can, by convexity, we can take the average inside the exponent that I have in here. So this 3 to the minus w is an exponential. I can take the average inside the exponent at the expense of turning my equality into an inequality. And then this gives me an upper bound. And this upper bound depends only on the average weight, which is a very kind of easy to compute quantity. So the average weight of my operator is approximately given by its average size multiplied by its average density. Meaning, to a first approximation, it's like on every site that's in here, I have the same average density. And okay, in reality, there's going to be kind of boundary effects and so on, but I don't care to a first approximation. So once I have this, I can very easily minimize my upper bound. And I find that by using the solution that we found in the previous slide, we find this solution for the optimal depth, which has this form here, with this gamma is the rate of relaxation that we can compute. And then there is a leading logarithmic term, logarithmic in k, which agrees with the qualitative observations that were made in those previous papers that I mentioned at the beginning. And then we have this sub-leading term, this minus 3/2 log log, which again is really not that important because it's really small, but it has this signature 3/2, which comes from this power law. So it's a really a signature of this random walk picture for the solution, and we're going to check it. So that's interesting for that reason. Okay, so then I can, let's see. What happens as a function of time is summarized in this picture, basically. So we have this upper bound, that's the curve in black that I just mentioned, that is minimized at this depth, which is logarithmic in k. And if we plug it in, we find that the optimum, the minimum value of the upper bound is given here, and it's close to up to kind of smaller corrections, 3⁻⁴ k. So this is, if you compute 3⁻⁴, it's this number here, roughly 2.28, which tells you that, again, this is an upper bound, so you're doing significantly better than the random Pauli measurements of the scaling of 3 to the k. And this is completely rigorous. This is there's essentially no approximations going into this. And we can have this separation, the significant improvement over the random Pauli measurements. But then we can go beyond this upper bound and try to actually solve the problem. And we can do so within some approximation that I'm not going to go into any details on, but essentially we have very good arguments for the fact that the optimal scaling achieved at this depth should actually be close to 2 to the k, which is really as well as you can do. So this lower bound is a kind of what would happen if you only had relaxation with no spreading. So it's a best case scenario, it will give you 2 to the k. So we're getting very, very close to that. And okay, so this was all kind of analytical, but we have some numerics that is showing good evidence of this behavior that I've argued for. So these are MPS simulations, so a kind of tensor network simulation, not simulation of the true dynamics, but of some effective model where we already average over the unitary gates, which makes it a lot easier and more tractable. And this way we can look at infinite systems and huge Pauli operators up to 1,000 sites. Again, this is not practically relevant because nobody's ever going to measure a 1,000 site Pauli, but it's a test of our theory, and it's a test with a very high resolution, and we can see that comparing our mean field approximation to this data, it's actually very close, particularly at late times. And we can further test the scaling of the optimal depth, and we find that it's in very, very good agreement with this scaling here, so the log k, but also this subleading correction, which we can actually fit, and we find a coefficient that is very close to the prediction of 1.5. So this is very good kind of parameter-free evidence that our understanding, our kind of approximate analytical theory for this is actually correct. So this 3/2 again comes from the random walk picture for the relaxation of density. Okay, so I think I have do I have 5 minutes?
You have more if you want. Okay. We started around 10, so you have 10 minutes.
Fantastic.
But we can extend a little bit.
Okay, great. No, that should be plenty. So this is what I wanted to say about this part. And again, if there are questions, I'm happy to answer them. But in the time remaining, I wanted to briefly flash some other recent results that are closely related in the following sense. In the sense that shadows are a way of... Sorry, question?
Just one, if you could go back a few slides.
Yeah.
You said that the optimum depth would be given if we just have a relaxation, right?
Mm-hmm.
Without spreading. Is this possible though in this scenario?
Right. So it's not in a real random circuit. It's not. You can have both. So what I'm saying here is that if you're allowed to cheat, let's say that you can cheat because somebody tells you in advance that you're going to want to know only some operator that is supported on some particular segment of k sites. Mm-hmm. Right? So normally you don't know this, so you have to be completely agnostic and treat all the sites as equivalent. But if you could know in advance, you could just take those k sites and do a random Clifford on those k sites without coupling them to the others. So then you have relaxation and no spreading. And then the random Clifford result was 2 to the n, if you recall. But in this case, n would be k, so that would be 2 to the k.
Okay.
So basically, by cheating, you could do 2 to the k, and this is really close to that. So it's essentially saturating this lower bound.
All right. Thank you.
Yeah, that's a good question. Okay.
Sorry, I have a quick question.
Yep.
So in your discussion about the relaxation, does it rely on the two-gate Clifford unitary you apply if it's more than two cubic gate?
I see. Yes. So here we only use the two design properties. So it doesn't care whether it's Clifford or Haar, but it cares about two design, and it cares about the architecture. So if it's nearest neighbor 2-qubit brickwork, this goes through. If it's more than 2 qubits, I don't think that it does. It may be the case that the solution is similar, but the proof as we did it doesn't work.
So the two design is the reason that you can use the random walk. Is that right?
So yes. So I mean, the two design implies that this picture goes through. I think that it's not necessary strictly, but there are gates you could use that would break this picture. Yes, some swap gate with some. Yeah, it's possible to break this picture.
I see.
With some choice of gate ensemble. Yes.
Okay, thank you.
Yeah, good question. Okay, so essentially shallow shadows are one approach for bridging between the locally randomized measurements that you would get for t equals to 0 and the globally randomized measurements that you would get for t equals to infinity, and you can tune t to go between them. There is a different thing you could do, which is instead based on tuning the locality of the measurement basis. So you could have, you could allow yourself to do measurements that are entangled over n qubit subsystems or clusters, so that you could get the random Pauli measurements for n equals to 1, where there's simply no entanglement, and you could get the random Clifford measurements if you allowed for entanglement on the entire system. And then you could change this, this subsystem size, little n, to go between them and see what happens, whether that gives you any advantages for things that you might be interested in. So to give you, very quickly an example of how this might work, you can take n equals to 2, meaning that you allow yourself entangled bases only over pairs of qubits. So to do this, you have to first choose, a pairing of qubits. So you have to form pairs between all the qubits in the system, and that's what I'm going to call a dimer covering. This is from condensed matter physics, I guess. You have a lattice, and you choose pairs of sites to be combined, to be paired together, which you can do many different ways, and you might have, different goals might benefit from different choices of dimer covering. But here I'm picking a simple one. Just to show the idea. And then for each dimer, you have to choose the measurement basis. And here you have a lot of freedom. But for example, let's choose the Bell basis, which is made of these 4 states that are maximally entangled. So it's a kind of extreme choice where random Pauli measurements would be disentangled and this maximal entanglement. So let me also define compatible operators as those that intersect each dimer either 0 times or 2 times. So schematically here, it's the operators in green. Could be this string operator, or it could be this kind of product of pairs like this, or anything like that. Whereas the red operators are incompatible because they are breaking at least one of these dimers. For example, this triangle here is breaking this dimer. This singlet is breaking this dimer, and so on. So the result we find in this paper is that the shadow norm of such a Pauli operator is going to be either infinite if the operator is not compatible, meaning that there's no way to learn it. Like this infinite is kind of an abuse of notation to say that it's impossible to learn. But in the cases where the operator is compatible, the behavior is extremely good. It's this 3 to the k over 2, which is quadratically better than the random Pauli measurement, but it's also better than the shallow shadow result that we just found, 2 to the k. And this is really a bit puzzling because we just argued that at the optimal depth you could achieve 2 to the k. So this Bell measurement you can think of as a depth 1 circuit, and it's very, at first sight, puzzling that you could do better than 2 to the k. So this 3 to the k over 2 is basically square root of 3 to the k, which is 1.7 something, so it's better, right? The loophole is that in shallow shadows, we always assume that there are random Cliffords both before, sort of both on this side, kind of hitting the state, but also on this side, right before the measurements. And in this particular protocol, we don't have that. We have random Cliffords only at the beginning, not at the end. And that basically breaks that mapping that we discussed on operator weight, and it allows us to basically do better or worse, like better in some cases, worse in some others. And again, I want to emphasize that this kind of trade-off where you do better in some cases and worse in some other cases is inevitable, because in this original paper, it was shown that 3 to the k is the best you can do if you are completely general. Like the best protocol that has certain scaling on all possible Pauli operators has to be at best 3 to the k. So you can only improve on some operators if you do worse on some others. But nonetheless, this is sometimes worth it because we care a lot about some particular types of operators often in many circumstances, and it could be beneficial to kind of improve the learnability of some operators, even if you do worse on others. Okay, then very briefly, I showed you the case of Bell measurements. You can change the amount of entanglement in the basis, and you can define a whole family of this kind of protocols with 2-qubit entangled bases, and you can interpolate between the Pauli measurements that have 0 entanglement and the Bell measurements that have maximum entanglement. For example, with this parameter delta, that's kind of the deviation from maximum entanglement. And here you can see the behavior for a family of these protocols, and basically there is this very large discrepancy between even and odd k, because odd k is breaking one of these dimers, whereas even k is not breaking any. And this discrepancy gets kind of smaller and smaller as you increase this parameter delta, at the expense of making the scaling a little bit worse, going from 3 to the k over 2 sort of progressively towards 3 to the k. But many of these protocols could be quite useful. And then finally, last thing I want to say is that if you further allow yourself to entangle more qubits, it turns out that the GHZ basis on n qubits, which is this kind of cat state basis with let's say all down plus or minus all up, and variations of that, completing that to a basis, that allows you to achieve an even better scaling of 1.5 to the k, which I'm schematically showing here along with the others. And this is very efficient. It basically allows you to, for a fixed sample budget, learn the expectation of operators that are a lot bigger than you could do with either Pauli measurements or even with shallow shadows. There are some caveats, in particular that the operators that are compatible with this are fewer and fewer, the larger you make your number n. And also these GHZ measurements can be a bit expensive in the sense that they require depth that is linear in n to be implemented. So again, there's some care to be taken on noisy hardware, but in principle, this gives you very efficient access to that particular class of operators that you can learn. Okay, so with that, I want to close. So just as a recap, I've given you a view of classical shadows. We presented this work on shallow shadows and how we can try to understand their performance by connecting it to operator weight under random dynamics with this competition between spreading and relaxation, obtaining these results summarized here. And then briefly, I've sketched this idea of locally entangled shadows, where we can use a different property, not operator spreading, but the structure of entanglement in the basis to improve performance in some cases that might be interesting. And okay, I want to thank my collaborators, Yaodong, Tibor, and Vedika, and also, of course, thank you very much for the very good questions, and thank you for your invitation to speak. And I'll take any more questions you have.
Yeah, thank you very much. It was a great presentation.
Thank you.
very clear, very nice. Good colors as well.
Thank you.
So I don't know if the audience has any more questions for a speaker.
Thank you for the very nice talk. I really enjoy it. So I have further question for your last part of your talk. Do you mean you do not use the general to design gates? You just apply specific gate which are compatible to the timer structure?
Oh, I see. Yeah. So here, for example, let's take this case of n equals 2, which is the easiest. I want a 2 design for these local rotations. So these could be Cliffords or Haar or some other 2 design on the single qubits. And after that, I have a deterministic circuit here. So these gates here are controlled Z if you want to do Bell states, or could be a controlled phase with a variable angle that would interpolate between no entanglement and maximum entanglement. And then, this is just a Hadamard and Z measurements. This just means, do an X measurement. And then if you put this whole box together, this is a measurement in the Bell basis. So that part has to be non-random for this protocol to work.
I see. Okay.
So fixed circuit. Yeah.
Okay, it's fixed. I see. And so another question is about usually how can we deal with some noise? I mean, if there is noise in this case, so do we have to better understand the noise model than try to find the optimal way?
Right. Yeah, that is a great question. Something that I think is very interesting. I know that there are a couple of papers that exist on classical shadows with noise, but I think that they are thinking about kind of random Pauli measurements and measurement error mainly. So here we have a more complicated setting, in this case and even more so in the other case, where there will be noise throughout this circuit. And that will be more complicated because then the effect of noise can spread. So that I guess I don't have a great answer, but basically it's possible to write down this kind of, let me go back to the definition of this channel. It's possible to write down here what this channel would be. If you would put here, instead of the U rho U dagger, you would put some channel acting on rho, which describes the noisy implementation of U. And then the question is, what would be the best thing to put here as your snapshot? Should you put the kind of your noiseless ideal estimate, or should you try to guess the noise model and put some noisy state here? Yeah, I actually haven't thought about that problem, but it's a very interesting one. And whether that still gives you a non-zero optimal depth, yeah, unclear.
I see. Thank you.
Yeah, it's a very good question.
Do we have more questions? Okay, I think that's it then. Let me thank you one more time, and let me stop the recording.
Okay, yeah, thank you so much again, and thanks for all the very nice questions through the talk.